Uh, uh, Today, I would like to discuss about synchronization primitives. Why do we need synchronization primitives? And different synchronization techniques are we going to use in a HPC? Right. Okay. Uh, I think from the last two classes, last two sessions, we are discussing about OpenMP and MPI, right? Okay. In OpenMP and MPI, we are working with multiple threads. When we are working with multiple threads, do we face any problem in a multi-threading environment? Any guess? Any guess?
There might be something like race conditions or which thread will, how much amount of work will be divided to which amount of thread, such kind of.
Yeah, usually one of the main problems is data races, right? What is
Yes,
a data race? If, one of the threads or one of the concurrent threads perform the update operations. Okay, those update operations should be visible to all other threads. Okay, if those update operations are not visible to all other threads, then there is a data race problem. Okay, on that particular data race problem, I would like to give a very simple example. Try to understand that particular example. Are you able to see the screen?
yes,
Are you
sir.
able
Yes,
to?
sir.
Okay. Yeah, this is simple OpenMP code, right? Okay. When we look at the purpose of this particular code, okay, we declared a variable X. After that, um, we considered few statements. OpenMP set underscore num threads. What is the purpose of that particular statement?
We are fixing the threads.
Yeah, we are
First.
fixing the number of threads. Okay. We are fixing the number of threads in this particular for loop, right? We are in this particular for loop, we are performing increment operation. We are incrementing the X value by 1. Okay. Right. Here, all the threads are together performing how many increment operations? 1 lakh operations. All the threads together performing 1 lakh operations. Okay. Suppose when we try to print this particular result, okay, we are going to expect 1 lakh on the screen, right? Okay. So now what I'm going to do is I would like to execute this particular piece of code. Do you know how to execute this particular piece of code? This is simple OpenMP program written in C. We can execute it by using gcc openmp3.c minus omp3. This is the executable. Okay, so to compile OpenMP code, we have to use the flag minus f OpenMP. Yeah, it is successfully compiled. Now I'm going to run that particular executable OMP3. When we look at this particular one, what is printed here? What is printed here? What is the expected value? Here, what is the expected value?
So 1 lakh should be expected, right?
Yeah, 1 lakh is the expected value, but it prints 28,272. That means, again, suppose if you execute that particular program one more time, it prints a different value. That means, actually, based on this particular example, okay, we can we can conclude that then there is a problem with this particular piece of code. That particular problem is data race problem. That problem is data race problem. How can we address that particular data race problem? Any guess?
With synchronization.
Yes, with the help of synchronization. Okay, good guess. In OpenMP, anyhow, actually, you have some idea about OpenMP, right? Hash pragma.
Can kind of give something like critical, right?
Yeah, hash pragma OMP critical. Yeah. Now we are going to execute this particular one with help of that. That means actually this hash pragma OMP critical defines a lock on that particular statement. Suppose if you want to define a lock on set of block of statements, you have to put open curly brace and closed curly brace across the set of statements. Okay. When we put the statement on the top of required one, what will happen is we are going to define a lock on the top of that. Okay. That is a critical section. Okay. In that context, only one thread will be allowed into the particular critical section. Only one. Here we are working with 4 concurrent threads, but that particular update operation is performed by the only one thread at a time. Now we are going to
But sir,
execute. Yes. Please go
for
ahead.
for this scenario, like if I understood Dr. Saurabh correct, like atomic is more better option than critical, right?
Yeah, that is also right choice. But when we are working with only one variable, suppose if you are working with, no. Atomic, hash pragma atomic, right? What you said that, right?
Yes, because yeah,
Atomic means it is executed by only one thread, right?
atomic means like the variable is atomic, and he mentioned like if you are just executing one, it's for like
Okay, you suppose.
computations, not for
So,
like certain number of lines. Basically, critical is good for when you have multiple number of lines that you want
yes,
to execute, and atomic is good for when you are doing such kind of operation
good,
only, like that you
good.
have mentioned x equals to x plus 1.
Yeah, what you said is correct. Okay. But I would like to give a simple toy example. That is why I considered this simple critical section, right?
Yeah, that's fine. This is for the clarity I asked.
Yeah, sure. What you said is correct. Suppose when we execute this particular one, actually here you can clearly observe that output is 1 lakh. Output is 1 lakh. That means that particular data race problem is addressed. Okay. To address that particular data race problem, okay, we can address that particular data race problem either by using atomic operation or by declaring a critical section or declaring critical section for a given set of statements.
The critical section means that only one thread is calculating that
Yeah,
accessibility.
yeah, means that here what is going to be happen is, okay, this block of code is in critical section, means that only one thread will be allowed into that particular critical section at any point of time. Okay. Suppose if more than one thread wants to enter into that particular one has to exit. Okay. The thread which is there in the critical section should exit first. Then only other thread will be given priority to enter into the critical section.
Okay.
Did you get my point?
Yes.
Okay.
So like in the for loop, what is happening is that like multiple threads are getting multiple processes, like no,
Yeah.
multiple threads are getting to do the summation in different like
Yes. Here what will happen is here when we look at, suppose consider without OMP critical. Here what is the operation? Operation is x equal to x plus 1. This is the operation, right?
yes.
X equal to x plus 1. Okay. Suppose without OMP parallel for this statement supposed to be executed 1 lakh times without that particular OMP parallel for, right?
Yes.
Yeah. Now when we are working with 4 threads, what will happen is that this entire work is divided among these 4 threads. Suppose consider there are 4 threads T0, T1, T2, T3. In that context, usually 25,000 operations performed by one thread. Another thread also performs 25,000 number of operations and so on.
Yes.
Okay. So in this context, what will happen is suppose consider this thread performs the operation x equal to x plus 1. Okay. X equal to x plus 1. This second thread also performs the operation x equal to x plus 1. When we don't declare it as a critical section, okay, what will happen is suppose consider initial value of x value is 0. Okay. This thread performs the increment operation on 0. This thread also performs increment operation on 0. Then actually both the threads independently work on that particular one. Then X value, after some time, X value becomes 1, right? But if both the threads execute those two statements to one time each, okay, then X value is supposed to be 2, right? Okay, here problem is, suppose update operations performed by the thread T1, okay, are not visible to the T0 and vice versa. Okay, in that context, we will get the problem of data race. Okay, to avoid the data race, what we have to do is we have to consider synchronization primitives. We have to consider synchronization primitives. Are you with me?
Yes.
Yeah. Here, similarly, how can we achieve synchronization primitives? By using critical section. Usually what will happen is, okay, here actually everything will be done by that particular OMP code. Okay. So what can I do is, are you able to see the screen, right?
Yes.
Okay. Yes. Here I would like to give you one more simple example. Okay. Actually, this program is written in Java. Suppose if you are comfortable with Java, you can easily understand this particular one. Vi counter.java. When you look at this particular one, counter.java function, here what can you see here? Here there is an increment method. Here there is an increment method. In increment method, what are we going to do? We are incrementing the count value by 1. We are incrementing the count value by 1. Okay. Here, to understand this particular one, we should have some idea about what is that. Okay, when you look at this particular node consists of one variable, int dot count. Okay, whenever we create an object of type node, okay, that particular count value is initialized with 0 here, right? Okay, after that, whenever we perform this particular increment operation, count value is incremented by 1. Count value is incremented by 1. Are you with me? Is there any problem while understanding this particular one? No problem, right? Here we are going to display this particular result on the screen with the help of that. Okay. Here, when you look at this particular piece of code, here I'm going to execute this particular one without using logs. Okay, there is no log at all. If we don't consider any log at all, and I'm going to execute Java C counter.java, there is no problem. I wrote a wrapper class here. Okay, that is a counter test. No problem at all. I think you are able to see the screen, right?
Yes.
Yes,
Okay. Java C, Java counter test. One thread, and the second argument is the time, how much time you want to execute. That is actually, this is 1000 milliseconds, that is 1 second. When you are working with, when we execute 1000 milliseconds with the help of one thread, there is no problem. Total number of operations is this much. Okay, whenever that particular thread performs this many number of operations, head dot count value should be the same as this total number of operations. Both should match, right? Okay, suppose instead of one thread, if we execute the same program with 2 threads, yes, total operations, those 2 threads together perform this many number of operations. Okay, but when we look at the head dot count value is this one. That means that in this particular program, there is a data race problem. There is a data race problem. Okay. Suppose consider instead of 2 threads, you can run with 4 threads. Then also you will get the similar kind of problem. Total operations. Thus 4 threads together perform this many number of increment operations. But head dot count value is this much. Okay. So there is no match between those two numbers, right? So then there is a problem, data race problem. To overcome that particular data race problem, what we have to do? We have to consider a lock. Okay, lock is a synchronization primitive. With the help of that particular synchronization primitive, we can avoid the data race problems. Okay, suppose consider this particular one. Java C. Okay, I think that I need to remove this particular lock. Here, lock is of type reentrant lock. Okay, if you want, you can create your own locks. Most probably in the next sessions, Mr. Brahmaya will discuss about different types of locks. Okay, there are different types of locks. Okay, spin locks and Q locks. Yeah, he will provide in detail discussion on spin locks and Q locks. Now I'm going to recompile one more time. There is no problem at all. Now, when I use one thread, there is no problem. Here, total operations is this much, and node dot count also the same. Both are same. One thread, there is no issue at all. When I consider 2 threads, 2 threads also, see that total number of operations is this much, and node dot count is both are same, right? Are you with me? Are you with me?
Yes.
Yeah. Not only 2 threads. Suppose if you increase to instead of 2, if you consider 4 threads, then also we'll get the correct answer, right? Here, based on this particular example, okay, what can we say? Okay, when we are working with multiple threads, to avoid this data race problems, okay, we need, okay, synchronization primitives. Okay, we need synchronization primitives. What are the synchronization primitives? Usually we have to consider locks and barriers. Locks and barriers. Barriers concept actually in the last session, while discussing MPI programs, I discussed about barrier, right? Okay. Barrier is a point, okay, at which, okay, fastest thread should wait for the slowest thread. Once all the threads reach to the particular point, then only threads will be allowed further to execute some other tasks. Are you with me? Is there any doubt? Are you with me? Hello?
Yeah.
Yes, sir.
Yes, sir. Yes, sir.
Okay. Okay. Right. Now, I'm going to discuss a little bit theory on this particular one. Okay. When we are working with multiple threads, okay, there is a need of synchronization. Okay. Yes, two or more threads contend for the same shared memory location at the same time, and at least one of them updates the memory location. Okay. Then data race problem occurs. Okay. To avoid that particular data race problem, we need synchronized primitives. Okay. Yes. When we look at the synchronization primitive, usually we are going to consider locks and barriers. Okay. Locks. Usually, when we are talking about locks, uh, to avoid this particular data race problem, usually we will consider mutually exclusive lock. Okay. Then means that if one thread enters into the critical section, okay, remaining threads, the one thread enters the critical section, remaining threads either should be in ideal state or waiting to enter into the critical section. Okay, you should not be allowed more than one thread into the critical section. Okay, while designing any lock, okay, we have to take care of something else. Okay, key issue in designing any lock is what action to take when trying to acquire a lock which is already held by the another thread. Okay, that defines the performance of the lock. Okay, there are many types of locks. Okay, TAS lock is there, T-TAS lock is there, Peterson lock is there. Just like that, many locks are there. Okay, suppose for small number of threads, you don't find that much difference. As we keep on increasing the number of threads, suppose if you are working, suppose you want to write a multi-thread code for 4 threads or 8 threads, any lock is fine. Suppose if you are working with 48 threads, 96 threads, and 192 threads. In such kind of scenarios, lock design also impact the performance. That is why we have to consider appropriate lock. Not only that, okay, in the last session, I discussed about, okay, UME architecture, uniform memory access, and NOMA architecture, non-uniform memory architecture, right? Okay, in uniform memory, some locks are suitable for UME architecture, and some locks are suitable for NOMA architecture. Okay, based on the need, we have to consider appropriate lock. That is about locks. Next one is barrier. Barrier is a synchronization primitive, okay, that halts all the threads at a given point in the code, okay, and allows them to proceed only when all the threads have arrived at that particular point. Okay, suppose which type of applications need this kind of barriers? Suppose when we are playing a video game, right? When we look at this particular video games, okay, usually nowadays 80 frames per second is going to be displayed, right? Okay. In that context, suppose to display 80 frames per second, okay, multiple threads should work in some coordinated manner, right? Otherwise, one frame, okay, is going to be mixed with the other frame. Usually, suppose we are going to display 80 frames per second. In that context, frame numbers are frame 0, frame 1, frame 2, and so on, frame 79. Okay, if we properly done that particular application, frame 0 can be mixed with frame 1 or frame 2. Okay, in that context, instead of seeing one particular figure or particular image, we can see some other one. Okay, that is the problem, right? So to avoid such kind of problems, we have to properly consider the barriers. Barrier is a kind of halting point for all the threads. Once all the threads complete that particular task, then only those threads will be allowed. Okay, I would like to give a very simple example for that barrier. Suppose you consider this particular screen. Okay, here I am going to divide screen into uh, right, so 16 parts. Okay, here okay, number from 0, 1, and so on 15, and so on 15. Okay, for each part, one thread is responsible to display the image in this particular part. Okay, another thread is responsible to display the image in this particular part. Okay, image in this particular part, and so on. Okay, in that context, what will happen is, we suppose that that is the frame in actually one frame. Okay, suppose if you want to display the another frame and another particular timeline, what we have to do is, first of all, we have to display all this image. Then only these threads will be allowed to display the another frame. Okay, once all the thread display the another frame, then only those threads will be allowed to display the next frame, and so on. In such type of applications, we need a layered approach. We need a layered approach. Are you with me? Is there any problem while understanding this? If
No,
there
sir.
is any, no problem. Next one. So while working with these multiple threads, okay, usually we have to take care of 2 things. Okay, first one is safety property. Second one is liveness property. Safety property means usually bad things never happen. Okay? What are the bad things in a particular multi-thread environment or multi-core environment? Bad things in a multi-thread environment and multi-core environment is possibility of deadlocks, right? When we are working with multiple threads, okay, then we may enter into a deadlock situation. Okay, so we have to avoid such kind of deadlocks. We have to avoid such kind of deadlocks. Okay, not only that. Okay, one more bad thing is we may enter into data race problem. So we have to avoid data races by using some means. Okay, either by using logs or by using barriers. Suppose if we are smart enough, okay, we can write log-free algorithms. We can write log-free algorithm without using logs. Also, we can perform the operations. How can we perform the operations without using logs? By considering atomic operations of the atomic operations. Okay, usually bit test and set and compare and swap or LLSC, load, link, and store conditional. Okay, these are the instructions provided by the architecture. With the help of those instructions, okay, we can write lock-free operations. We can write lock-free operations. Are you with me? Not only that, to write the lock-free operations, we can consider some beautiful algorithms. With the help of those algorithms also, we can write lock-free operations. Here, I would like to give a simple example for this particular barriers and how to write the uh, this lock-free approach. Okay, how to use this particular one. Are you with me? Do you have any problem while understanding this particular one? I hope that you don't have any problem, right?
No, sir, with you.
Okay. Yeah. When we look at this particular one, hmm, here when we look at this particular logic, what can you understand from this? It is difficult to understand from that particular one. Okay, I can agree with you. This is simple one is I'm going to calculate a power n. A is a matrix of order so and so. I'm going to calculate a power n of a matrix. A power n of a matrix. To calculate a power n of a matrix, what can be done? First, we can compute a power a square. After that, we can consider a barrier. After that, we can consider a cube. This is simple nav implementation. Don't worry about efficiency of this particular one. Next, we can compute a cube, a power 4. Okay. Suppose if you don't put the barrier, what will happen is we may end up with wrong result. Okay. That is the simple program. Okay. How I did here, when you look at this particular one, here you can see that I consider one simple barrier, that is sense barrier. That is a sense barrier. After that, this is the simple logic to perform the matrix multiplication. You know how to perform the matrix multiplication, right? Next one is, this is a simple function uh, to copy back, okay, one matrix into the another matrix. Suppose if result is available in C, okay, I want to copy back from C to B. I can do that particular copy with the help of this copy function. This copying also can be done by using multiple threads. This copying also can be done by using multiple threads. Okay. Next, when we look at this particular run method of a thread, here what I did, Okay, suppose if I want to calculate, okay, if I want to calculate a power n, that is a power, okay, okay. First of all, I'm going to multiply this particular one with the help of thread ID. Later, we are going to wait some time here. Later, again we are performing the copy operation. Next, again there is a barrier here. We are going to repeat these many number of steps. Okay, these steps some number of times. Then we will get a power n, a power n. Okay, right. Here, when we look at this particular one, yes, Verbi dot is different matrix. What are the arguments of this particular one? When you look at this particular matrix, or here we are passing three arguments. First argument is the number of threads. The second argument is the order of the matrix. And third argument is the power. Third argument is the power. Here, what are the initial elements of this matrix? We are going to initialize uh, these matrices with this particular matrix with 1. Then we can easily verify the result. Okay. When we look at this particular one, my matrix operations.java, there are no problems at all. Java, my matrix operations. When number of threads is 1 and order of the matrix is 4, we are going to calculate a square. This is the result. Okay. Are you with me? Are you with me?
Yes, sir.
Okay. That means that here what we did, we performed this particular one, actually this multiplication twice, right? Okay, this one. That means not square. When we look at this particular one, okay. So I think I did a mistake here. Yeah. Suppose if we calculate initial value of A, matrix A is all the elements are initialized with 1. Whenever we perform that particular A square, this is the case. After that, whenever we compute A cube, these are the results for A cube. Whenever we compute A power 4, these are the results for A power 4. Are you with me? Are you with me? Suppose here, what is the matrix? Matrix is all the elements are, that is the matrix. All the elements are 1, 1, 1, 1, 1. Okay. This is the A square, A cube, and A power 4. Here, what we did, we consider the barrier. When we consider the barrier, we can execute it in, yes, suppose if we are going to execute this particular one without using barrier, let us see what will happen. There is no barrier. Here, barrier is sense barrier. Here, barrier is a sense barrier. Okay. Here, number of threads is 1. 1 means no, we don't have any problem. And we work with 2 threads. Let us see the results. See the results. Did you find the problem? When we work with 4 threads, until we observe the different results, right? There is no consistency. Did you find any consistency here? Hello? Hello?
Yes, sir.
There is no consistency, right? To overcome this particular problem, what we have to do is we have to consider the barriers. To overcome that particular problem, we have to consider barriers. Yes. Suppose if you right, if you execute it with the help of 4 threads, we can see execute with the help of 2 threads, execute with the help of 3 threads. Okay, all the time we got the correct result. Okay, that is why when we look at this particular implementation, here this particular one is a lock-free implementation. Here we haven't considered any locks at all. When you look at the multiplication logic, here what I'm doing, I'm calling a particular method, right? Multiply with the help of thread ID. Multiply with the help of thread ID. When we look at that multiplication logic, what can you understand from this particular multiplication logic? When we look at this particular one, this is a simple mm, uh, a lock-free implementation of matrix multiplication, right? Here, what do you mean by that? Okay, uh, when we look at this particular one, okay, here this is the matrix. Assume that this is matrix B. This is matrix A. Okay, this is matrix A. Assume that matrix of A of order 100 cross 100, 100 cross 100. Matrix B of order 100 cross 100. We are going to multiply these two matrices with the help of 4 threads. With the help of 4 threads. In that context, okay, yes, thread 0 is responsible. Those 4 threads are T0, T1, T2, T3. These are the 4 threads. These are the 4 threads. Here, thread T0 is responsible to get the first row in the result and 26th row in the result, and what can we say? Next one is first row. Next,
74.
no, 26, 50,
50.
50, 51. Next one, 76th one, right? Okay. Yeah. Yes. Well, suppose when we are working with 4 threads, what can we say? Actually, these rows are divided among these 4 threads. In that context, simple logic is T0 is responsible for 100 mod 4. If 100 mod 4 equal to 0, okay, in that context, for all those rows, T0 is responsible. If 100 mod 4 equal to 1, for all those rows, P1 is responsible. Are you with me? Not 100 mod 1. Actually, here instead of here 100 means my intention is here 100 means this is the row number. Row number varies from this is the row number. Okay, this is the row number. Okay, when we vary this particular row number, if row number value is suppose consider row value varies from 0 to 99. In that context, 0 mod 4 is 0. So T0 is responsible to get that particular one in the that particular row in the resultant matrix. At the same time, if row number is 4, 4 mod 4, then also it is 0. Then T0 is responsible to get that particular row in the resultant one. If row number equal to 8, then also 8 mod 4 equal to 0. Okay, just like that is an example, right? When we look at this particular logic, okay, in this multi-thread context, we haven't considered any locks. For some applications, okay, if we carefully manage the particular data and uh, concurrent threads or multiple threads, we can perform that particular multiplication without using locks. Without using locks, that is the beauty, right? How the data is where is the data? Okay, how many number of threads do we have? Okay, how to partition the work among these threads? Okay, at any point of time, multiple threads are going to work on the same data or not. If multiple threads are not going to work on the same data, our job is very simple. Simple and straightforward. We can, without using locks, we can simply partition the entire work among the threads and complete the task. Are you with me? Are you with me? Do you have any doubt while understanding this particular one? Here, when we look at this particular simple matrix multiplication, we multiplied the two matrices, A and B matrices, without using locks. Here, there is no locks at all, right? How we did it? Okay, here simple thing is, if consider simple thing. Okay, I would like to give one more simple example. Simple example is, we have two 4x4 matrices. Two 4x4 matrices. We want to multiply these 4x4 matrices with the help of 4 threads. That is thread 0, thread 1, thread 2, thread 3. Okay, thread 0 is responsible to multiply this particular row with all these columns. All these columns. Next, thread B is responsible. That means thread 1 is responsible to multiply this particular row with all the 4 columns. Then get one thing at the same time. Thread 2 is responsible to multiply this multiply this particular row with all these columns. Okay. So when we look at this particular multiplication, no thread overlaps with the other thread operation, right? No thread overlaps with the other thread operation. In that context, we can easily write lock-free algorithms. We can easily write the lock-free algorithms. In that particular scenario, we don't need locks at all. Are you with me? Are you with me?
Yes, sir.
Yes. Yeah, here main logic is, here we carefully selected this threads, this particular variable. Threads is the number of threads. Here TID is the thread ID. Usually when you are working with thread ID, 4 threads, thread ID varies from 0, 1, 2, 3. For thread ID is 0, initial value is 0. It picks a row with row index 0. After that, for that particular thread, next I value is 0 plus 4. Okay, 4. Next value is for the same thread, 8 and so on. For thread ID, which has thread ID 1, in that context, I equal to 1. All are independent, right? Okay, here this particular one, okay, this is independent. In that context, what will happen is, for that particular thread ID, I equal to 1, I equal to 5, I equal to 9, and so on. Just like that, okay, we can compute this particular entire operation with the help of multiple threads or concurrent threads. Are you with me? Is there any problem while understanding this particular simple program?
Sir, understood.
Yeah.
Sir, why do we need this? Like, is this second multiply just to show, or like,
Which one? No, this is the sequential implementation. That is sequential logic. You know, you have some idea about how to perform the sequential implementation, right? Here, when we look at this multiply operation, we haven't passed any thread ID as an argument, right? When you look at the upper one, in the upper one, we pass a thread ID as an argument.
Right. Got it.
Okay. At the same time, usually for copy operation also, we can do the normal copy. At the same time, we can perform the copy operation with the help of multiple threads, with the help of thread ID.
Right.
Yeah.
Understood.
Okay.
Sir, can you show the matrix multiplication example using that lock and lock
Barriers, right?
like the previous one that you were showing, like, before this, not using locks or barriers.
Yeah, before this, actually, I showed one example, that is simple increment operation by using locks. Do you need that?
No. Do you have a matrix multiplication using locks or something?
Yeah, that also can be done. But I haven't considered that particular one here.
Okay.
I haven't developed a code for that. Oh, if we want, we can do it. That is not a big issue.
So for in that, if like somebody writes a code in using locks or barriers, so when we send the each row to different threads, You have to wait for each threads to synchronize and then like add it together.
Yeah, that is true. You know how to write this particular matrix multiplication logic in OpenMP?
Yes, sir. Like, it was done.
Yeah, that is very simple and straightforward, right?
Yes, sir.
Yeah, that's it. Did I answer your question?
Yes, sir.
Okay. Yeah. So when we are working with multiple threads, okay, we should have some idea about what are the synchronization primitives. Okay, that means what are the locks are there. Okay, when we are talking about locks, okay, yes, actually, what is the mechanism behind this particular lock? Is it good for a given architecture? Suppose if you are using a UMA architecture, some locks consider CLA, CLH lock is good for UMA architecture, uniform memory architecture. Okay. At the same time, MCS lock is good for NOMA architecture. Okay. At the same time, TAS lock is good for when we are working with 3 or 4 processors. Okay. TAS or TTAS is good for 3 or 4 processors. You heard about Peterson lock. Okay. Peterson, when we are want to design a simple Peterson lock, we can design a simple Peterson lock. Okay, all these lock designs will be explained in the next session. Okay, today I'm giving a brief introduction about these points. Okay, after that, okay, for something, suppose here also, if we want to design our own barrier, we can design our own barrier. Here I explained, we designed our own sense barrier. Okay, I explained that particular piece of code with the help of that particular sense barrier. We need these synchronization primitives. Suppose if you don't want to use these two, then we can use the atomic instructions provided by the architecture. What are the atomic instructions? Bit, test, and set. Okay. Cas, compare, and set. The third one is LLSC, load linked and the store conditional. By using those are atomic exchange. Okay, some atomic instructions are there. If you are good at microprocessors, you can use those atomic instructions. Okay. Usually, as part of my course that is in microprocessor interfacing, usually we will use this particular atomic instructions to exchange the data between 2 variables. Next one, while designing any concurrent program or any parallel program, okay, we have to take care of 2 properties. First one is safety property. Safety property is very, very important. When we take care of safety property, then only our code is correct. Okay, in the safety property, we have to take care of 2 things. Okay, that is mutual exclusion property. What is mutual exclusion property? In uh, in a critical section, only one thread will be allowed into the critical section at any point of time. That is the mutual exclusion property. Next one is deadlock free property, right? What is deadlock free? Actually, when we are with multiple threads, we never enter into a deadlock state. We never enter into a deadlock state. That is very, very important. Okay. How when do we enter into deadlock state? Suppose consider a linked list. Suppose when we are performing the operations on a linked list, someone is suppose if we allow one thread to traverse from left to right, and if we allow another thread to traverse from right to left, in that context, then there is a possibility of deadlock. Okay. To avoid that particular deadlock, we have to follow some particular ordering, lock ordering. Otherwise, definitely we enter into the deadlock state. Okay. Next one, third one is that is optional. That is fairness property. Okay. When we are working with multiple threads, okay, we try to achieve fairness among the waiting threads. Fairness among the waiting threads. Otherwise, some threads may have infinite waiting time. Okay. And actually, that is not at all suggestible. That is why, while suppose if you want to design a lock, we have to design a fair lock. It is always not possible to design a fair lock. Okay, but up to some extent, we try to achieve the fairness among the waiting threads. Is it clear? Okay. Next, after that, okay, usually in HPC implementations are divided into uh, two types. Broadly, we are going to classify the implementations into two types. Okay, blocking-based implementation and non-blocking implementation. What is meaning of the word blocking-based implementation? Okay, if one thread is delayed, if suppose due to some reason, if one thread is delayed, all other subsequent threads are going to be delayed. Okay, then it is called a blocking-based implementation. Blocking-based implementation and non-blocking-based implementations. Non-blocking means if one thread is delayed, only that thread is going to be delayed. All other subsequent threads can comfortably perform their operations. Then such type of implementations are called non-blocking implementation. Are you able to understand these two terms? Because these two terms are very, very important terms in HPC. Do you have any doubt? Please clarify your doubts.
So can you explain the different, like the definitions in
Difference, right? So, here I would like to give one simple example. Okay, when we are working with multiple threads, right? Suppose this is a simple linked list. Linked list consists of some set of nodes. Okay, this is one node, this is on one another node, this is another node, this is another node, and so on. Okay, suppose thread 0 is traversing from left to right. Thread T0 is traversing from left to right. Okay, in that particular process, thread T0 reaches to this particular point. Okay, due to some reason, OS suspends this particular one. OS can suspend any thread at any point of time, right? That is not in our control. After that, thread T1 wants to perform some operations on this particular one. Again, it is going to verify all these nodes. In that particular process, actually, if this T0 okay, stops the execution of thread T1, okay, then such kind of implementation is called a blocking based implementation. Because of T0, thread T1 cannot proceed further. Because of T0, T1 cannot proceed further. Okay, in that kind of implementations are called blocking based implementations. Okay. Are you with me?
this?
Okay. Next, suppose suppose here consider another scenario. This T0 is suspended due to some reason, but T1 will be allowed to perform operations on the next node. Suppose in this particular node, when T0 is in suspended state. Such kind of scenario, such kind of applications are called non-blocking based application. That means one thread is not going to block all other threads. One thread is not going to block all other threads. Okay, that is non-blocking based implementations. Okay? Usually, blocking based implementations are divided into deadlock free and starvation free. Okay, that means this is the basic bare minimum requirement when we are working with multiple threads or in HPC environment. Our implementation should be a deadlock free. Okay, here in the deadlock free, we don't bother about fairness. Okay, fairness among the waiting threads or fairness among the threads. In starvation free, we have to we have we have to give the fairness among the threads. Okay, we have to satisfy FCFS property among the waiting threads. Are you with me?
Yes.
Okay. In lock-free implementation guarantees that here we are not going to use any locks at all. In lock-free implementation guarantees that, okay, execution is going to be terminated after finite number of steps. Okay, guarantees that execution is going to be terminated after finite number of steps. Okay. Yes, here we are not giving any guarantee on after how many number of steps execution is going to be terminated.
Sir, in wait free and lock free, there is a guarantee that we will get the output. But in blocking, is there any? So if one thread is killed or something, then if
No,
it
no,
is
no, no. The thread should not be killed in between. Right? If thread is killed due to some reason, okay, in that context, other subsequent threads should take that responsibility. Otherwise, we may end up with wrong results.
Okay, okay, sir.
Okay, actually, in such kind of scenarios, other subsequent threads should take care of the responsibility of those threads or pending tasks of the previous threads.
So in blocking, there is a chance that we may not get the result also. So it will
No,
be
no,
keep
no,
on running.
no. If we don't get the result, our implementation is wrong.
Okay, okay.
If we don't get the result, simply say we did. That means we do sometimes. There is a possibility to enter into the live lock. Okay, I haven't touched the live lock. There are
Okay,
two types
okay,
of
sir.
lock. One is deadlock. Second one is live lock. Live lock is
Okay,
a different scenario.
okay, okay, sir.
Okay, right. Usually in wait-free implementation, we are giving a guarantee that yes, this method is going to be terminated after this many number of steps. Okay, that is a wait-free implementation. Okay, designing or giving a wait-free methods is very hard task. Okay, let us say it is a really difficult problem designing wait-free implementations in a concurrent in HPC environment. Okay, this is easy one, deadlock-free implementation, but wait-free implementation is really hard. Suppose if you reasonably have good knowledge, we can try for these things, right? Starvation-free or lock-free implementations. Okay. Next one, usually in concurrent implementation or HPC environment, we have to give some guarantees. Actually, these are the theoretical guarantees. Actually, this is concept of linearizability. Concept of linearizability. Okay. Uh, yes. Linearizability means we have to give the two guarantees. That is, first one is sequential consistency and second one is quiescent consistency. Okay. We have to say that execution is sequentially consistent. And we at the same time, we have to say that execution is quiescently consistent. Okay. What is sequentially consistent? Sequential consistency says that it is not allowed to reorder two invocations belonging to the same thread. That is sequential consistency. Okay. Next one is quiescent consistency. What is quiescent consistency says that? Quiescent consistency says that not allowed to reorder two invocations that are separated by the quiescent period. Quiescent period is a period during which process is idle. Okay. Right. I would like to explain that particular quiescent consistency by considering very simple example. Try to understand this particular example. If you look at this particular one, here we are working on two threads, thread A and thread B. Okay, X is a shared variable on that particular one. X is a shared variable, Both are working on that particular shared variable. What are the operations on thread A is going to perform on X? Initially, it is going to perform write operation. Next is going to perform read operation. Next is going to perform one more read operation. Okay. Here, this thread B is going to perform only write operation. Suppose this is the timeline. Horizontal row is the timeline. This is the time during which process is idle. This period is called a quiescent period. This period is a quiescent period. When we look at this particular one, okay, these three operations are overlapped with each other, right? This operation is overlapped with this operation. At the same time, this operation is overlapped with this operation. Okay. These two operations are overlapped with each other. What can we say that in quiescent consistency, we are saying that, okay, it is not allowed to reorder invocations that are separated by the quiescent period. Means that this is the quiescent period. It is not possible to reorder this one and this one, or this one and this one. Okay, but we can reorder these overlapping operations in any order. Okay, in that context, we can clearly see one in that particular shared variable. We can clearly see one in that particular shared variable. Are you with me? How it is possible? How it is possible is How is that possible? If you look at this particular one, if thread B performs write operation at this particular point of time, this is a timeline, right? Okay, X is performing read operation here. When X performs the read operation at this point of time, clearly thread A can see the write operation of thread B. Okay, after that, here X is the thread A performing the write operation on X. Okay, the write of 1. If thread A performs the write operation on X, at least that particular same thread can see the 1 after some time, right? And see that particular value after some time. So when we look at this particular one, this particular execution is quiescently consistent, but not sequentially consistent. Why? When you look at this particular execution, is quiescently consistent, but not sequentially consistent. Why? Okay, when we look at the definitions of quiescent consistency and sequential consistency, quiescent consistency says that not allowed to reorder two invocations that are separated by the quiescent period. This is the quiescent period. So it is not possible to shuffle the operations that are performed after this quiescent period and before this particular quiescent period. Okay. These are the overlapping operations, right? These overlapping operations can be executed in any order. Okay. If any one of those orders yields this particular result, that is okay for us. That is okay for us, right? Okay. But what is quiescent consistency says that? Quiescent consistency says that not allowed to reorder two invocations belong to the same thread. Two invocations belong to the same thread should be executed in the same order. Here, what we did, we swapped these two methods. If you want, you can cross-check it. When we look at this particular one, okay, what is the initial condition here? When you look at this particular one, initially we are performing x dot write operation to the variable x. Okay, after that, within this particular thread A, after some time, it is going to perform the read operation. Okay, x dot read. Okay, when it performs the read operation, it observes 2. Yes, do you want to say something?
So just also like what are those numbers in the bracket?
Bracket means, suppose write means in that context, thread A is going to write
One.
one into that particular shared memory location. Okay,
So
when it
okay, so I have a question like how is thread B? Okay, no problem. Sir.
okay, yeah, actually here quiescent consistency says that these three operations can be executed in any order. Why? These three operations are overlapped with each other, right? This one is overlapped with this one is overlapped with this one. In that context, when you are working on a single core mission, these three operations can be executed in any order when that particular mission is designed based on a quiescent consistency.
So
But
how so like if I suppose like you were saying that these three operations can be executed in any order. Suppose if I change the position of x dot write 1 and x dot read 2, then it will not make any sense. Okay? Because you're reading 2 before thread B has written 2.
pardon?
Suppose I exchange in thread A, I exchange it to order x dot write 1 with x dot read 2. Okay.
Okay.
So then like thread A will first perform x dot read 2 before thread B has written 2, like x dot write 2.
Yeah, suppose at this particular time it performs the x dot write 1, right? At this time it performs x dot write 2. At this particular timeline, it performs x dot read 2, right? When we look at these three operations, when we consider those three operations, that is perfectly valid, right? Okay. But overlap, these threads can be executed in any order. That is the quiescent consistency. Okay. When we look at our memory models of our systems, our models of the system is relaxed memory model. Okay. No system is implemented based on sequential consistency. If our systems or laptops are implemented using sequential consistency, actually performance of our laptops is very slow. Okay. Okay. That is why quiescent consistency says that, see, when we look at this, not allowed to reorder two invocations that are separated by the quiescent period. That means this is the quiescent period of the processor, when we look at the timeline of this particular this is the timeline of the processor. When we look at the from the processor perspective, okay, from this particular timeline to this particular timeline, everything is occupied, right? Are you with me?
Yes.
Okay. From this particular point to from this particular point, everything is occupied. Processor is occupied with some or other operations. Okay. So within this particular timeline, what is going to happen? These methods, this method and this method is overlapping with this one. In that context, these methods can be executed in any order. That is not in our control. That is not in our control. That is the beauty of multi-core programming or multi-threaded architectures. When they do that in that way, then only we'll get the better performance. Okay. No processor will be designed based on sequential consistency. It will be designed based on some other consistency, relaxed memory consistency. Okay. But when we are going to write a HPC multi-thread codes in HPC environment, we have to consider order among the threads. That means if you look at this particular order, thread A, initially thread A performs the write operation. After that, the same thread A performs the read operation. We have to respect this particular thread order in our HPC environment. Are you with me?
Yes.
Yeah. Yes. Within a thread, okay, which consistency gives the that particular guarantee? Sequential consistency gives that particular guarantee. Sequential consistency concentrate on only single thread. See that sequential definition of sequential consistency. Not allowed to reorder two invocations belonging to the same thread. Okay, sequential consistency talks about operations performed by one thread.
So that means that for thread A, if we are not sequentially consistent, then X dot read 2 would have come before X dot write 1.
Yes.
Because
Then only we can observe this particular one by thread A.
Okay. But that would not make any sense because thread B then would not have written like.
No. Someone, that is why when we look at the comment, when we look at the caption of this particular figure, I clearly mentioned that this particular execution is quiescently consistent, but not sequentially consistent.
Oh, okay. Yes.
I clearly mentioned here, right?
Yes.
Next, I would like to give one more example here. When you look at this particular example, this is sequentially consistent, but not quiescently consistent. How? This particular example is sequentially consistent, but not quiescently consistent. How?
So suppose if I in the period where like in the question period where X dot write 1 has
No.
thread.
No, sequential consistency gives a guarantee on order of the execution, right? You should
Yes, sir. So actually, write first, write one, write two, then read one. So the order is maintained.
Yes, that's true. So in sequential consistency, what are we going to do when we are working with multiple threads? Okay, these multiple threads need not respect these particular quiescent periods. If you are causing, this is the quiescent period during which processor ID, right? When we compare thread A and thread B, thread A and thread B need not respect this particular quiescent period. Okay, when we think only about quiescent consistency or sequential consistency. Sequential consistency gives the guarantee. Suppose thread A is here, thread A is going to perform two operations, write and read operations. Okay, sequential consistency says that that particular thread should perform those two operations in that particular order, program order itself. It is not allowed to reorder those operations. That is quiescent consistent. Okay. So if we suppose when you look at this particular example, sequential consistency but not quiescent consistency, when we look at this particular execution, okay, how we can see that, okay, here what we did, initially we performed these two operations. After some time, we are going to perform write operation on the particular shared variable X. Okay. This is perfectly valid when we are talking about only sequential consistency. Okay. In HPC environment, suppose in that particular environment, we have to give both the guarantees. Okay, what are the guarantees? We have to give the sequential consistency and quiescent consistency. Then only our execution is correct. Okay. Any execution gives such type of guarantee, then only we can say that that particular execution is linearizable. That particular execution is linearizable. Okay. Here, when you look at this particular one, what can you see that? Here you can see that this is the quiescent period. This is a quiescent period. Okay. See, uh, these threads, these three operations, these three threads are overlapped with each other. In that context, one of those overlaps should give this particular result. That means whenever one of those overlaps gives that particular one, that means whenever thread A performs the read operation on X, it observes the 2, then it is correct. Then it is correct. So in what way it can be executed? When you look at this particular one, suppose thread A performs the write operation at this particular timeline. After that, thread B performs the read operation at this particular timeline. Okay. Yes, write and read. When a thread A performs the read operation first at this particular timeline, and thread B performs the read operation. In that context, the thread B can comfortably observe one in that particular shared memory location. After that, after some time, thread C performs the write operation that particular timestamp. Okay. So now there is a quiescent period. After that, this thread A performs the read operation on X. Then it comfortably see the 2 during that particular read operation.
Sir, how to decide the quiescent period, sir?
No, quiescent, that is why quiescent period is not in our hand. Quiescent period means period during which processor is idle. That
Okay.
means processor is idle means nothing to do during this time. That means all these three operations can be executed in some order, right?
Yeah, any order. Yeah, it can be
Any order.
executed. Yeah.
Yes. That is not in our hands.
Okay.
A quiescent period means period during which process is idle. That's it. That is the quiescent period.
Okay. Okay. So, but
Sir,
sir, actually, not allowed to reorder. So,
Yeah.
before this quiescent period, it is not allowed to reorder the instructions.
So when we look at this particular execution, we haven't reordered the operations of thread A. Here, thread A is going to perform two operations, write
Yes.
and read operations, right?
Yes.
Okay. So we haven't reordered those operations. Then we don't bother about sequential consistency. Here,
Yes, sir. Yeah.
thread A satisfies sequential consistency. Anyhow, thread B
Yeah.
and thread C performs only one operation each. Then we
Yes.
don't bother about sequential consistency. Next, we have to bother about quiescent consistency. So which period is the quiescent period? This period is the quiescent period. Okay. So yeah, all the operations, that means these three operations can be overlapped in some order. Okay. If these threads overlapped in some order and that yields to this particular result, that is okay for us.
Okay.
sir,
Yes.
sir, what does the length of the line mean? Like this,
Yes. Length of the line is, that is the width of the time period, right? Usually this particular, when we look at this particular one, this is the function, right? Write operation. Okay, to execute write operation, actually in a parallel in a concurrent environment, HPC board, that write operation can be performed at any point between these two boundaries. Length, that particular backline gives the boundary, it gives the interval to perform that particular operation. Interval to perform that particular operation. That particular method can be executed during that particular interval at any point of time.
which
Did
is
you get?
assigned by the OS.
Yes, they assigned by the OS. That is not in our
Okay,
hands.
then it makes.
Yeah.
Okay, then it makes sense.
Okay.
So that means the system can just take care of the ordering itself within like these
Yes.
overlaps, basically.
Yeah, overlaps at the same time. Sometimes we have to be very careful. Suppose if system does not take overlaps, we have to explicitly put the barriers at some places. Suppose when we are working with multiple threads, if we need this particular one, we have to keep the barrier here. Okay. If system takes care of that particular thing, that is fine. If the system does not take care of thing to get the desired output, in that context, we have to keep the barrier here.
Right.
Yeah, that is about this particular one. In the next, actually must take a break for at least 10 to 15 minutes. Please be back by 7:30. Okay, in the next session, I would like to discuss these different synchronization techniques. I would like to discuss all the synchronization techniques by considering simple data structure linked list.
Sir, can I ask one question?
Yes, please go ahead.
In the previous to previous slide,
Okay.
this slide, no, next slide, next.
Okay.
No, next slide again. This.
Okay.
No, the next slide. Sorry, next. Where you showed the last, like the last example that you are showing for thread, thread A, thread B, thread C.
This one.
So here, when we are for thread A, when we are maintaining sequential consistency, coefficient consistency is automatically maintained, right?
Yeah, but actually, suppose if we consider only sequential consistency, okay, and then we have to maintain this particular order, right? Okay,
Yes.
when we are talking about quiescent consistency, okay, these two operations can be interchanged in any order, right?
Yes, but for this particular case, maintaining sequential consistency automatically maintains coefficient consistency.
Yes, it automatically maintains. That is why I consider this particular example.
Okay.
Okay, did you get my point? Actually, for
Yes.
better understanding, that is why I consider this particular example.
Yes, sir.
Here, my point is actually this thread A respects the program order.
Yes.
Thread A respects the program order. Thread B, when you look at thread B and thread C operations are overlapped with operations of thread A. First operation of thread A. Okay. In this context, these three operations can be executed in any order. One of those interleavings lead to this particular result that is acceptable in parallel programming environment or concurrent environment.
Okay, sir.
Are you with me?
Yes.
Okay. Okay. Take a break for around 12 minutes. Please be back by 7:30. Hello. Good evening. Are you able to hear me?
Yes, sir.
Yeah. Now, I would like to discuss, till now we discussed about different synchronization primitives and different implementations of HPC applications, blocking based and non-blocking based. Okay, and how to define linearizability of any HPC application, right? Okay, linearizability means it satisfies both the sequential consistency and quiescent consistency. Okay, in the next 45 minutes and so, I would like to discuss about different synchronization techniques. Okay, usually we are going to consider 5 types of synchronization. Okay, coarse grain synchronization and fine grain synchronization, optimistic synchronization, lazy synchronization, and non-blocking synchronization. When we look at the coarse grain synchronization, means that we are going to acquire the log on large chunks of the data. That is called coarse grain synchronization. Next one is fine grain synchronization. If we acquire the log on small chunks of the data, then it is called fine-grained synchronization. I would like to give a simple example for these two. If we consider a data structure linked list, okay? Suppose if we acquire a lock on the entire linked list, then it is called coarse-grained synchronization. Suppose if we acquire a lock on node level, then it is called fine-grained synchronization. Next one is optimistic synchronization. Optimistic synchronization means we are going to identify the required set of the nodes without acquiring the lock on all its predecessors. Okay, and then we can save some amount of time. Okay, once we identify the required set of the nodes, we are going to identify the once we identify the required set of the nodes, we are going to acquire the lock on those two nodes. After that, we are going to verify that those nodes are reachable from the head node or not. That is optimistic synchronization. In lazy synchronization, we are going to identify the costly operations. Okay, we are going to while performing the costly operations, we are using lazy implementation of that particular method. Usually, when we consider that kind of implementation, it is called lazy synchronization. Okay. Anyhow, I'm going to discuss all those synchronizations by considering a simple example, that is concurrent implementation of linked list, because you people have some idea about a linked list implementation. That is why we consider that concurrent implementation. Next one is non-blocking implementation. In non-blocking implementation, okay, we are going to perform the operations on that particular data structure without considering the locks. That is non-blocking synchronization. Okay, first one is coarse-grained synchronization. When we look at the just a few minutes back, I told the definition of coarse-grained synchronization. Coarse-grained synchronization means we are going to acquire the lock on large chunks of the data. After that, we are going to perform the operations on that particular one. Consider this particular example. Here, this is a simple linked list. Okay. When you look at this particular simple linked list, what can you see here? Okay. This is the head node, and this is the tail one. Head node, and this is the tail one. This is the head node, and this is the tail node. Okay. All the nodes between these head and tail are in sorted order. This is a kind of sorted linked list. Now we are working with two threads, thread A and thread B. Thread A wants to perform insert operation, insert of 35. Thread B wants to perform delete of 10. Okay. In that context, actually now there is a competition between these two concurrent threads. When there is a competition between those two concurrent threads, one of them will succeed in the particular process, right? One of them acquired the lock on the head node. The thread which acquired the lock on the head node, that particular thread will be allowed to perform that we are going to allow that particular thread to perform the given update operation. In that context, where 35 is going to be inserted, 35 is going to be inserted after 30. Okay. Yes. So in that context, the thread A need not acquire the lock on all these intermediate nodes, because here in this coarse-grained synchronization, we are controlling the threads based on the thread which acquires the lock on the head node. Head is the starting point or entry point into that particular linked list, right? Based on the head only, we can traverse into that particular list. Are you with me? Is there any difficulty while understanding this particular simple one? Are you with me?
Yes, sir. No confusion.
No confusion, right? So now we are allowing thread A to perform the given update operation on that particular one. Next one. Once thread A performs the update operation on the particular data structure, it releases the lock. Once it releases the lock, now thread B acquires the lock on the head node. Once thread B acquires the lock on the head node, we are allowing the thread B to perform the given update operation. What it does, it is going to perform delete 10. When it performs the delete 10, it removes that particular 10 and it updates the link. Head next points to node 20. This is simple coarse-grained synchronization, right? Here, when you look at this particular this particular implementation, here we are working with two threads, thread A and thread B. and thread A is performing insert of 35. Thread B is performing insert delete of 10. In that context, to perform those respective operations, thread A and thread B, both the operations can be performed simultaneously or at the same point of time. But this implementation is not allowing to perform both operations at the same time. That means here this particular coastline synchronization restrict the parallelism. Okay, it is not allowing multiple thread to perform the update operations at the same time. Okay, that is the problem. How can we overcome that particular problem? We can overcome that particular problem by considering another synchronization, that is fine-grained synchronization. That means instead of acquiring the lock on large chunks of the data, we can acquire the lock on small chunks of the data. In linked list implementation, which is the smallest chunk? Smallest chunk is at node level. Suppose if we allow a thread to acquire the lock at node level, then we can perform both the operations at the same time. We can perform both the operation at the same time. That is fine-grained synchronization. Now, we can see that. Suppose consider next one. This is simple fine-grained synchronization. Here also we are working with two threads, thread A and thread B. Again, thread A is performing insert of 35. Thread B is performing delete of 10. Okay, now thread A acquires the lock on head. Once thread A acquires the lock on head, now thread A will be allowed to perform that particular insert operation. In that particular process, thread A has to traverse from head node to given predecessor. Here, to perform insert of 35, what is the predecessor to perform that particular one is 30. Okay, after 30 only we have to insert 35 because list is sorted linked list, right? In that process, thread A, okay, again acquires the lock on next node. Okay, in that context, when you look at this particular scenario, now thread A acquired the lock on head and lock on node 10. Okay, yes, 10 is not the required node for us. Okay, in that context, what will happen is thread A releases the lock from head and acquires the lock on node 20. Okay, and so on. Okay, in that particular process, thread A, right, in that once thread A releases the lock on head node, then thread B acquires the lock on head. Once thread A, after some time, thread A releases the lock on 10 also. Once it releases the lock on 10, now thread B acquires the lock on 10. When you look at this particular picture, what can you see that? At this particular point of time, thread A acquires the lock on node 30, thread B acquires the lock on head and node 10. Okay. Now, at the same point of time, both thread A and thread B can perform the update operations on the linked list. Okay. In that way, we can increase the throughput of that particular one, right? That is the beauty of fine grain synchronization. Are you with me? Do you have any problem while understanding this particular one? Do you have any problem while understanding this particular one?
It's clear, sir.
It is clear, right? When you look at this particular implementation, this is a kind of a blocking-based implementation. Why it is blocking-based implementation? Suppose consider this particular scenario. If due to some reason, thread A is suspended, okay, after releasing the lock on head, thread A is suspended due to some reason. If thread A is suspended due to some reason, okay, thread B is not allowed to acquire the lock on node 10. Okay, right? Are you with me? Okay,
Yes,
Yes,
sir.
sir.
that is a kind of a blocking based. Here we don't have any problem with the thread B, but thread B is delayed because of thread A. Okay, thread B is delayed because of thread A. So it is a kind of a blocking based implementation. Okay. Now I discussed two methods.
One doubt
Okay.
here, sir.
Yeah.
Uh,
Please go ahead.
Sir, if I have a lock on, let's suppose A has lock on 10, okay,
Okay.
and wants to do something with 20 or 30, so can we jump through A and go to 20, 30?
No. Actually, here in fine-grained synchronization, it uses kind of hand-over-hand locking mechanism. suppose how it is traversing, right? It is traversing actually in this particular fine-grained synchronization. Suppose to perform the update operation on node 30, it has to identify this thread A is going to acquire the lock on all its procedures. If it is not the intended one, then it releases the lock. Otherwise, first of all, it has to acquire the lock on that particular one and verifies that whether this one is the required node or not. If it is not the required node, then it releases the lock from that particular one.
So then one doubt I have here is, one question it raises is that I'll be acquiring, let's suppose if my linked list is really big, then I'll
Yeah.
be spending more time in just locking, unlocking, and other threads keeps checking it, right? So we'll be wasting a lot of CPU cycles here.
Yeah,
right?
CPU cycles, but to achieve the correctness, this is the best choice.
Yeah, that is to there for that no race condition happens. For that we have to do this, right?
Yeah, no, yes. Yes, actually, otherwise we have to write some other methods to verify that particular race condition. We can overcome this particular problem in optimistic synchronization.
Okay. Thank
Okay.
you.
Okay. Right. Now I would like to show the code for these two implementations. I think these two implementations are clear to you, right? Is there any problem?
Yes, sir. Clear.
Clear. Okay. Yeah. I think you are able to see the screen, right? Are you able to see the screen?
Yes,
Yes,
sir.
sir. Visible.
Okay. When you look at this particular one, here what can you see here? This is the course list class. Here, when you look at this particular one, here we are considering two sentinels, that is head and tail. Head is initialized with minimum value and tail is with maximum value. Okay. After that, okay, here when you look at this particular one, here one more variable is there. Think about this particular one. So line in line number 9, you can see that lock is a variable, okay, of type lock. Okay, in that particular lock variable, we are storing the object of type reentrant lock. That means with the help of this particular variable, we can call some of the methods which are there in the reentrant lock class. Okay, what are the methods what are the methods available in the particular reentrant lock class? Reentrant lock class, okay, so two methods, two of those methods which are there in reentrant lock class are lock and unlock. Lock is used to acquire the lock on a specific object, and unlock is used to release the lock from that particular specific object. Okay, where is this particular this particular variable? This particular variable is there in that particular course list, right? Whenever we create an object of type course list, okay, we are going to use with the help of that particular object, we can use object of type reentrant lock. Okay, whenever we call lock.lock, then we can acquire the lock on that particular course list object. Whenever we call lock.unlock, we can release a lock from that particular object. Okay? Those are the methods. After that, when you look at this particular one, this is the add method to perform insert operation on the linked list. Okay. Similarly, this is the remove method to delete a node from the linked list. Okay. This is the simple contains operation to perform such operation on the linked list. When you look at this particular, all these three operations, okay, here we are calling the lock method. After that, we are performing the required operation. After that, we are calling the unlock method. Okay. Similarly, you can see the method. Suppose in remove operation also, to perform that particular remove operation, we are acquiring the lock. That means we are acquiring the lock on the entire object. After that, we are calling this particular unlock. Okay. Similarly for add method also. Okay. After that, we are going to test the performance of this particular course list implementation by considering wrapper class. Here I consider the wrapper class as list test.java. When you look at this particular list test here, when you look at this particular one, I'm considering instance is a variable of type course list. Here I considered course list object. I'm going to check the performance of that particular one. Here, when we look at this particular list test constructor, I'm passing some number of arguments, right? What are those arguments? First argument is number of threads. Second argument is range of values. In a concurrent, in HPC environment, we cannot test the performance on a small data structures. Okay. Test the performance of particular application on linked list of length 5 or 10. Okay. List should be sufficiently large, and on the top of it, we had to consider different workloads. Okay. By considering the different workloads and sufficiently large list, then only we can check the performance of that particular implementation. Okay. When we look at how can I execute this particular one? To execute this particular one, first I'm going to compile this particular list.java. Okay. I compile list.java. Okay. Are you able to see the screen? Is there any problem? No
No,
problem,
sir.
right? Okay. Now I'm going to run this particular one, list test. When you look at this particular list test, when I consider one thread, number of threads is 1, and actually length of the list is the range of the keys is 2000. 2000. I'm going to execute this particular one in around 10 seconds. That is 10,000 milliseconds. We are going to pre-fill this particular one is 50%. Here range of the keys is 2000. That means range of the keys comes from 0 to 2000. And we are going to pre-fill that particular data structure with 50% of the elements. In that context, length of the linked list is at least 1000 nodes. Okay. And at the same time, here workload is 50 and next workload is 75. 50 and 75 means that here, when we look at the characteristics of this particular workload, this is very important when we are working with multiple threads in HPC environment. Here, the reason is that, okay, suppose each thread is going to perform some number of operations within this stipulated time period. Here, time period is 10,000 milliseconds. During the 10,000 milliseconds, okay, it is going to perform X number of operations. Okay. Out of this particular X number of operations, some percentage of operations are contains operations. Here, 50% of the operations are contains operations. This is the meaning of this particular 150. Okay. After that, when we look at the difference between this 50 and 75, it is 25. 25% of the operations are insert operations. Okay. Remaining 25% is the delete operations. That is the workload, that particular explanation about that particular workload. Okay. Here workload is 50C, 50% contains, 25% insert and 25% delete. Okay, now I'm executing this particular one. Okay, pre-filling is done. That means it creates a linked list of length 1000. After that, it is going to be executed around 10,000 milliseconds. It is 10 seconds. When the number of threads is 1, here when you look at this particular output, here implementation is course list implementation. Implementation is a course list implementation. Here throughput is 0.49. That is millions of operations per second. Total operations is this much. Okay. Time is 10 seconds, right? In that context, here when we have to divide this particular one with 10, we'll get operations per second. When we divide that particular one with 10 power 6, we'll get millions of operations per second. Okay. Right. Usually we are going to call it as MOPS. Okay. For the same implementation, if we try to execute with 2 threads. When we try to execute with the 2 threads, you can see that we observe the less throughput. The reason behind that is these 2 threads continuing to acquire the lock. Okay, that is why Postgres implementation creates a contention at the head node. That is the problem. Not only simultaneous execution of the threads. These threads can create a contention. Okay, that is why we have to avoid such type of scenarios, or we have to avoid such type of implementations. Okay. Next, to actually similarly now instead of course list implementation, I would like to execute the same program with a fine list implementation. Here instead of course list, here I would like to consider fine list implementation. Enter this particular one. This is the fine list fine list instance. This is the fine list instance. Okay, I would like to comment this particular one. Now I'm compiling one more time. Okay. Now I would like to execute. First one is the number of when the number of threads is 1. When the number of threads is 1, more or less we'll get the same output. And sometimes you will get the better throughput from the Postgres implementation when the number of threads is 1. Here you can see that here throughput is 0.11. Okay, that is fine. But as we increase the number of threads, let us see. When we increase the number of threads, when we increase the number of threads from 1 to 2, what will happen? Yes, here a little bit improvement. Okay, we are not happy with that. Instead of 2, I would like to consider 4. Let us see what is going to happen. Yeah, here also a little bit improvement as compared with single thread implementation, but this is not up to the mark. Here problem is in fine grained implementation, we are going to acquire the lock on all its predecessors. To acquire the lock on all its predecessors, so much time is going to be wasted, right? That is why we got the very less throughput. That is why we got the very less throughput. How can we overcome that particular problem? We can overcome that particular problem by considering some other implementations. Here, I would like to show the execution first. Later, I will explain the theory behind that. Okay. Later, I would like to consider lazy list implementation. I think it is free. Lazy list implementation. If we can Java C list test, and the number of threads is 1, and the number of threads is 1. We got 0.3. It is a little bit close to the course grain implementation. Fine. We are increasing the number of threads from 1 to 2.
So what is TP?
Pardon?
What is TP? Like,
Prefill means prefill means actually when we are working with
no, sir. TP.
TP means throughput. TP means throughput. Throughput means actually number of operations per second. Here I'm calculating millions of operations per second. How I'm going to calculate millions of operations per second? Here, how many number of operations we perform in a particular stipulated time period? What its value? What its value? Its value is 6 million, right?
Yes.
Okay. In that context, 6 million per 10 seconds, right? What is the operations per second? 6 lakhs.
Yes.
Closer to, right? Are you with me?
Yes. Yes.
6 lakhs per second. So 6 lakhs operations per second means if I divide this particular 6 lakhs with 10 power 6, that is a million means 10 power 6, right? Okay. So its value is 0.6 millions of operations per second, MOPS.
Okay.
Millions of, that means if you multiply this particular 0.6 with 10 power 6, you will get this particular value. Suppose simply multiply this value with 10 power 6,
Yes.
you will get that particular value. Here, see, here you can clearly see when the number of threads is 2, there is improvement, right? Did you get that? Here,
Yes,
number
yes.
of threads is 1, it is 3.3.6. Number of threads is 2, it is 6.3.
Yes.
So here the ops is 63 lakhs, right? Not 6 lakhs.
Ops is no, ops is 63 lakhs. Here time is 10 seconds, right?
Oh, okay, got it. I got
Okay.
confused there.
Okay.
Thick, got it.
Next, if I suppose instead of 2 threads, if I execute with 4 threads, see how the actually is scalability of this particular application. As we increase the number of threads, we'll get the better throughput, right? See that. Here you can see 0.83. Instead of 4 threads, if we increase to 4 to 6, let us see any improvement. Yeah, here it is 1.4, right? Did you see that? This is 1.4 millions of operations per second, right? Did you get my point?
Yes, sir.
Yeah, suppose here, as we say, hardware is same. This is my laptop itself. My laptop is a 8-core laptop. Okay, here I am increasing the number of threads from 1 to this particular one. Up to 6, it is increasing. Suppose if we increase beyond 8, let us see what will happen. Suppose here I am going to increase instead of 6, I would like to consider 8. Okay, then also we'll get a little bit improvement or more or less same output. Yeah, here it is 1.5. Suppose if we increase beyond that, usually we don't get any better throughput. Reason behind that is there is hardware limitation. Hardware limitation is number of available cores in my laptop is 8. See, when I work with the 16 threads, the 16 threads creates a contention. Why 16 threads creates contention? Because of hardware. Okay, when you type LSCPU, okay, if this is my laptop, right? This is total number of CPUs is 8. Our total number of physical cores is 4, and each core acts as supports the concept of hyperthreading. So total number of cores is 8. Are you with me? Are you with me? Is there any
Yes, sir.
problem?
Yes.
Yes, sir.
Okay. Okay. Right. So now I would like to explain the reason behind that particular implementation. Yeah, I discussed the theory of this particular fine-grained implementation. In fine-grained implementation, we are going to acquire the lock on all its predecessors. Okay. So to overcome that particular problem, what can be done? To overcome that particular problem, what can be done? We can identify the target nodes or required set of nodes, or on which nodes we have to perform that update operation without acquiring the lock by using simple traversal techniques. Once we identify the required set of the nodes, what can be done? We can perform uh, we can acquire the lock on the required set of the nodes. Later, we are going to verify or we are going to retraverse from the head node. What is the need to retraverse from the head node? What is the need to retraverse from the head node? Any guess? Any guess?
So if you're calculating length or doing something with like last,
No,
last,
no, here, no, I would like to give a simple reason for that. Suppose here thread A. Here thread A, we are performing this insert operation by using optimistic synchronization. In that particular process, thread A identifies the required set of the nodes. This is the required node to perform the insert operation for thread A. Thread A identifies the required node. After that, okay, it identifies the timestamp T1. After that, the thread A acquires the lock at timestamp T2. During this particular time interval between timestamp T1 and T2, another thread may delete this particular node. Another thread may delete this particular node, right? Possibility is there in multi-thread environment or concurrent, right? In HPC environment. To handle that such kind of scenarios, what we have to do is, that means at timestamp T1, it identifies the node 30. Okay, at timestamp T2, it acquires the lock. Thread A acquires the lock on the required node. Okay, during that particular interval between T1 and T2, another thread may delete that particular node from the list. That possibility is there. To handle such kind of scenarios, we have to retraverse from the head node. If that particular node is deleted from the list, then when we retraverse it, we cannot see that particular node. When we don't see that particular node, something was happened during that particular time interval. Did you get my point?
Yes, sir.
Yeah. So actually, in concurrent programming or in HPC environment, when we are working with multiple thread, we have to handle all such kind of scenarios. Otherwise, we end up with wrong results. Okay. Right. In that context, what can be done here? Thread A is going to identify this is the required node to perform the insert operation. Okay. Once it identifies the required insert operation, it acquires the lock. Okay. After that, again, it has to retraverse from the head node, and if it is reachable from the head node, it performs the given update operation. If it is not reachable from the head node, okay, it releases the lock and again retraverse from the head node and then identify the new predecessor and perform the update operation on that particular new predecessor. Is it clear? Is it clear?
Yes, sir.
Okay. What are yes, please go ahead.
Sir, if we don't delete any element, if we just modify the values, then in that case, this most of the problems will get solved, right? Will not have any race conditions.
No. Usually, if that is the case, okay, means that that particular value is changed, right?
Mhm.
That means that particular value is updated.
Yes.
Okay. To perform the update operation, okay, uh, here there is a problem of ABA problem. There is ABA problem. Okay. Initially, it acquires the lock on the previous value. So, no. Actually, thread A identifies the node 30 on the previous value. But thread B, okay, modifies that particular value. Instead of 30, thread B changes 30 to 31. Okay. Okay. During that particular time interval. And after that, thread A again acquires the lock on the same value. Okay. Then such kind of problem is called ABA problem in the thread environment. While writing that particular these algorithms, we have to avoid ABA problem. That is a next level problem. Okay. I don't want to discuss ABA problem at this point of time. Okay. That comes under ABA problem.
Okay. Thank you.
If you have a textbook or a ChatGPT, please go through that ABA problem.
Okay, sir.
Okay. All right. So actually here one more problem is with this particular optimistic synchronization. What is the problem with this particular optimistic synchronization? What is the problem with this particular optimistic synchronization?
The retraversal is probably quite expensive, right?
Yes.
Repeatedly going through the list.
Yeah, absolutely correct. Actually, retraverse is going to take more amount of time. Okay. When it is going to retraverse, if we actually suppose in high contention workloads, right? That means high contention workloads, if some other threads quickly performs the update operations during that particular time interval, thread has to retraverse it. Even though it performs the retraversal, sometimes that particular thread may end up with unsuccessful retraversal. In that context, again, it has to release the lock and it has to perform the same operation again and again, right? It consumes so much amount of time. Did you get the point? Okay. That is the problem with this particular optimistic synchronization. Optimistic synchronization main problem is retraversal is the biggest problem in optimistic synchronization. Okay. Once we acquire the lock on a given node, we have to retraverse from the head node. If the length of the list is high, then we have to retraverse all its predecessors. It consumes so much amount of time. That is the problem with optimistic synchronization. How can we overcome this particular problem? We can overcome this particular retraversal by considering the extra field in the node. When we consider extra field in the node, we can overcome that particular problem. How can we overcome that particular problem? I will explain it in the lazy synchronization. Here, when we look at this particular example, okay, along with this particular, each node consists of two fields. Okay, those two fields are value and flag. If flag value equal to 1 means that particular node is there in the list. If flag value equal to 0 means that node is logically deleted from the list. Okay. Once it is logically deleted, later, after some time, we are going to delete that particular node physically from the list. Okay. Here I would like to give a simple example. Suppose we are performing a delete operation on this particular one. Okay. Thread B is going to delete the node 10. In that context, initially it acquires the lock. Once it acquires the lock on head and 10, initially it performs the logical deletion on this particular node. That means it simply updates that particular flag value. When it simply updates that flag value, okay, next it performs the physical deletion. It performs the physical deletion. Okay, when we use this particular approach, we can avoid retraversal. When we use this particular approach, we can avoid this particular retraversal. How? When we use this particular approach, we can avoid this retraversal problem. How? Any guess? Why are we performing retraversal? Why are we
deadlock?
no? Why are we performing retraversal? We are performing retraversal because some other thread deletes that particular node. Whenever some other thread deletes that particular node, then only we need retraversal. Otherwise, we don't need retraversal, right? Did you get my point?
Yes, sir.
Yeah. How to identify that particular one? Here, when we look at this lazy synchronization logic, okay, here deletion is divided into two parts: logical deletion and physical deletion. In logical deletion, we are updating the flag value. In physical deletion, we are removing or we are detaching that particular node from the list. Okay, in that context, suppose consider thread A identifies the required predecessor. Thread A is going to perform insert of 35. Thread A identifies the required predecessor 30. Okay, once it identifies the required predecessor, thread A is going to acquire the lock on this particular one. It is going to acquire the lock on this particular node. Okay, suppose it identifies the required predecessor, required node at timestamp T1, it acquires the lock on at timestamp T2. Okay, during this particular time interval, okay, some other thread deletes this particular node. What it does? First of all, it updates the flag value, right? Did you get my point?
Yes, sir.
During this particular time interval, some other thread deletes the node 30 that has to first update the flag value. Later, it has to perform the physical deletion. Whenever it updates the flag value, actually, this particular thread, after acquiring the lock, this thread simply verifies the its flag value of this particular node, right? There is no need to retraverse from the head.
Right. Yeah.
Yeah. In that context, we can avoid retraversal. In that context, we can save a lot of time. That is why you observed better performance as compared with remaining implementations. In lazy list implementation, just a few minutes back, I showed the results, right? In that particular lazy list implementation, you can see the better results as compared with the remaining implementation. Because of this simple trick,
Sir,
Okay.
then where exactly do we do the physical deletion, sir?
No. Here, yeah. Physical. Pardon? Repeat it.
Sir, we did logical deletion by
Okay.
marking the flag 1 from 0, right?
Yeah.
But it still exists in the memory. Now, if you want to do the physical delete, when exactly that happens?
No, after logical deletion, we are going to perform physical deletion immediately. After some time, immediately we are performing physical deletion. But
Okay.
this logical deletion avoids the retraversal. Because actually deletion is divided into two parts: logical deletion and physical deletion. In logical deletion, we are updating only flag value. See, first of all, here I would like to explain the logical deletion. When you look at this particular one, here thread A, suppose thread B is performing logical deletion. To perform thread B logical deletion operation, initially it updates the flag value. That means this particular node is logically deleted from the list and physically present in the list. Okay. After that, immediately in the next step is physical deletion. It simply updates that particular link. Okay. But this particular logic helps us to avoid retraversing. How it helps us to avoid retraversing? Suppose consider the case. Okay. Yes, before this particular node is going to be deleted, some thread identifies this is the required set of the required predecessor to perform some other operation. Suppose it is some other thread wants to insert 15. In that context, 15 is going to be inserted, 10 and 15. So this is a predecessor. It identifies the required predecessor at timestamp T1. Okay. At timestamp T2, it acquires the lock on this particular node. During this particular time interval, thread B performs the deletion operation. When thread B performs the deletion operation, some other, yes, this thread A need not traverse from the head node. It simply verifies, after acquiring the lock, it verifies its flag value. If its flag value is 0, means that some other thread deleted this particular node. There is no point to work on this particular one. Okay, instead of that, what it does is simply releases the lock and then only it retraverse from the head. Otherwise, in successful cases, there is no need to retraverse. In unsuccessful case only, we have to retraverse. Did you get my point?
Yes.
Okay.
Yes, sir.
Yeah, in that way, we avoid or we can save the search time. That is the beauty of lazy list implementation. When you look at the most of the implementations, they will lazy synchronization. Especially in lock-based implementation, most of the people either consider optimistic or lazy synchronization. In some cases, they will consider fine-grained synchronization. In some cases, they will consider fine-grained synchronization. Next, the last one is this one is non-blocking synchronization. In non-blocking synchronization, usually we are going to consider atomic operations. Those atomic operations are atomic compare and set. Okay, when you look at the compare and set operation, we are going to perform particular update operation atomically. That means if actual value equal to expected value, then we are going to replace this actual value with this update value. Then only we are going to replace that actual value with the updated value. Okay, this verification and this update operation, everything is in atomic. Okay, if that is the case, it returns true. Otherwise, it returns false. Suppose consider this particular example. Okay, here we are performing a delete operation. To perform a delete operation, we have to perform two deletes. One is logical deletion. Next one is physical deletion. In logical deletion, we are atomically updating this particular flag value. We are atomically updating this particular flag value. Okay, that is the first logical deletion. Okay, in physical deletion, we are atomically updating this particular link. We are atomically updating this particular link. That is the physical deletion. Okay, whenever we perform those two operations atomically, then that is a kind of a non-blocking implementation. First one, initially we are performing logical deletes by using simple cas operation. Next, we are performing physical deletion by using one more cas operation, that is compare and set. What can I do is, okay, today I would like to share all these programs with you. Okay, what you have to do is you can execute all these programs in your laptop or desktop. Okay, just execute it. Okay, do you have any problem? Okay, while understanding this particular piece of code? Okay, please let us know in the next session. Okay, we will try to clarify all your doubts in the next session. Are you with me? Is there any problem?
Sir, in the lazy implementation,
Okay.
is it possible that the node gets physically deleted before the process gets to check whether it was deleted or not?
No, no. In lazy deletion, that is guaranteed. First one is logical deletion, and the next one is physical deletion.
Okay, and the thread will get to check for logical deletion first, and then it will get physically deleted.
Yes, yes. That order should be maintained.
Okay,
Then only our implementation is correct. Otherwise, our implementation is wrong.
yeah, right. Okay.
Next one, I received a comment. That comment is, okay, hello sir, can you upload this? Yes, I think I uploaded the programs. I uploaded MPI programs. Can you check that? Are you able to access that?
Sir, I was getting access denied.
Access denied.
Yeah, I
Oh.
think it might be like a private folder.
Sorry. I will give the permission. Don't worry. Are you able to access the slides? Slides also no.
Slides are also private, I think.
Okay. Sorry. No problem. I will share it. That's it from my end. Do you have any specific questions? I'm here to clarify your doubts. If there are no questions, thank you.